So in the last lecture of Newton's laws, we were discussing about tension as one of the mechanical forces in, we were discussing about normal reaction as one of the mechanical forces in various kind of systems, and how it's a self-adjusting force as a contact force which acts perpendicular to the plane of contact. And by self-adjusting, we understood how its value can adjust according to the situation of other external forces. Now, another key type of mechanical force which figures out in most type of systems involving Newton's laws of motion we'll discuss today is the force of tension. So we will start with a bit of discussion about tension and a few example systems, and then we'll come back to the assignment and discuss the questions and doubts in that. So continuing on our discussion about the common mechanical forces, the common type of mechanical forces types. So the next type we'll see is tension. Okay. So tension is a type of force that develops along the length of a string, or rope or chain kind of situation, when it has a tendency to be stretched by external forces. So whenever a longitudinal material like a rope or a chain or a string is given a tendency to get stretched by external forces, it develops a force along its length, which is called tension. Okay. Of course, again, the at the molecular level, the tension is nothing but an electromagnetic force, because it is because of intermolecular interaction. But at the mechanical level or at the macroscopic level, we call that force as tension. And like normal reaction, it's a self-adjusting force. So let's understand this with a few examples. So the most basic example to understand tension is something like this. Suppose we have a situation like this, that on the floor, and there's some kind of a wall. Now we have, let's say, like a hook over here. Just a moment. And we have, to the hook, we have attached a string. Okay, very light. So its mass is negligible. Now, initially the string is, suppose it is lying, the string is lying loose on the floor with one end attached to the wall. Okay. So in this case, what is happening? We say that the string is lax or loose. So that implies that there is no tension. Okay. So that means there is no force along its length. There's no type of internal force along its length. Okay. But in the next situation, if we do something like this now, to the same string, Now next what we do is suppose we start pulling it from one end with an external force. Some external agent is applying some kind of a force. Okay. Now what will happen? The string will immediately develop. It will become, instead of being slack, or I mean this term loose, it is also sometimes called slack. So initially the string was slack, but now it will develop a tension. It will become tight. Okay. And as a result of that, we will see that it has a tendency of getting stretched. Okay. So what happens is, in terms of forces, the moment we apply external force on the string over here, there is a tendency for it to accelerate towards the right. Okay. But it's attached to the hook on this side. So the string develops, I mean, on the string, there are two mechanical forces that start acting. One is the force that the external agent is applying. Okay. And the other is from this end of the string where the hook is attached, there is a reaction force that develops. Okay. A reaction force that develops between the hook and the string. And that force, as it turns out, will be equal and opposite to this, because it's preventing, okay, the string from moving. But these two forces together, they give it a tendency to stretch out. So there is, this R is a reaction force, okay, at the hook in the wall. So this thing here is a hook. And what happens is, since the acceleration of the string is zero, okay, so the reaction force is equal and opposite to the external force we are applying. But the combination of these two forces, what it now does is, it stretches out the string. It gives it a tendency. So due to the forces F external from one side and the reaction force on the other side, the string has a tendency to be stretched. Okay. And it becomes, what we understand as, it becomes a tight string. So once it becomes tight, it develops an internal force along its length. So once it becomes tight, it develops tension, which is a force along its length. Okay. So this string is now pulled from one end by the external force, then this is what happens. Okay. So that tensional force, now it acts in this manner. That tensional force that develops along the string, it acts in this manner. Okay. So at this end, whatever external agent is pulling with the force F external, it experiences an equal and opposite force inward tension. The hook experiences an equal and opposite force inwards. Okay. And that tension that it develops, T, that T is equal to the external force, which is equal to the reactionary force. Okay, so just note down this most basic example of tension, and then we'll discuss more cases. Yeah, I shall explain that point. How we know that tensional force exists, the evidence for its existence, we'll discuss. Okay, so let's consider another basic example to also understand that how we can not only understand tension but also prove that it exists, and in fact even measure the amount of tension. Okay. So in my next example, suppose we have this situation. So we have from the ceiling, we have first attached, let's say, one of those spring balance kind of things in which we can measure. Okay, it measures weight, or basically it measures force by which it's getting pulled downwards. Now from the spring balance, we have initially attached, I mean, in the first situation, there is just a rope attached which is kind of hanging loose. So we have a rope. Mass m is tending to zero, means very small mass, maybe a few grams or something, and the rope is slack. So when it is slack, what will be the reading of this? Okay, the moment the rope is slack, what we'll observe is that the reading of the spring balance will be tending to zero. Okay, so what this shows that there is no pulling force on the balance. So that means tension is zero. The spring balance basically measures weight by measuring what is the pulling force here. Okay. So this force is tending to zero. So the reading is tending to zero. So the fact that we will actually measure that the reading of the spring balance is zero, we'll be able to measure that, shows that there's no tension in the string. Okay. But now the counter to this is that the moment we attach some mass over here, and then because of the action of gravity on that mass, what we see that the is that the rope that we've attached, it becomes, it goes from a state of being slack to a state of being tight. And the moment that happens, we will see that the spring balance is showing some reading. So that will give us the evidence that what is happening, there is some tension. Okay. And not only that, we will have one more evidence for tension, which I'm going to discuss. So now what will happen is, if we attach a mass to the string or the rope or whatever, okay, so we've attached a block. So immediately what we will see is that the rope is stretched out, and develops tension T. So that tension is going to be pulling this hook down with some force T. Okay, that tension is going to be pulling this block up with some tension T. Now, what is the evidence that tension exists? So first of all, we will observe that the spring balance now shows a reading, and that reading is equal to the tension in newtons. Okay. So for example, if the spring balance is showing a reading of 5 kg, so that means the tensional force in newtons is 5g. Okay, that's the first thing. Second thing is that if we look at the free body diagram of the block, okay, so on that free body diagram, we can see that weight is pulling it down. So some force has to balance that weight now, because its acceleration is zero. The block is at rest. So again, the evidence is that tension is equal to the weight of the block. Okay. So tension exists, and not only it exists, its amount is equal to how much? The weight of the block. So understood now, Ayush. Through this example, we can logically also understand why the tension in the string first of all exists, because what is keeping the block from accelerating downwards? There's only one other external force other than the gravitational force acting on it. That is the force that the string is applying on it. So the string must be having a force acting along its length, and that has to balance its weight. So it's a self-adjusting force. And if I replace the block with a heavier block, the tension will increase. If I replace it with a lighter block, the tension will decrease. And similarly, we can actually experimentally measure this tension also by just putting a spring balance on top over there. There is no normal force, na beta, because there's no surface of contact. The block is not lying on any surface. It's just vertically suspended. Ayush, normal force will exist na, only when there is contact between two surfaces. Yes, of course, that is correct, Nikita. So we will see that there is something called breaking stress. Okay. So if we go on increasing the mass that is suspended on that we are using the string to suspend, then at some stage, okay, the string will break at the weakest point. Gravity is an example of non-self-adjusting force. Manas. Okay. And yes, that point is correct. Rakshit, sorry, non-self-adjusting force, an example of it is gravity. Gravitational force does not adjust according to other forces. No, it's a certain mass m will always have a gravitational force mg acting on it. independent of whether we keep it on an inclined plane, on a horizontal plane, or suspended by a string, or suspended by a combination of springs, whatever. No, Ayush, let us not discuss about spring right now. We are talking about the string or the rope. Okay. Spring balance is just a device to measure the amount of force. No, not maximum capacity to stretch in that sense. The maximum tension the string can develop before it will break. That ultimately depends on the material of the string. Okay. Whether it is made of cotton, nylon, or it's steel wires which are blended together, all those kind of things. The material of the thread or rope or wire or whatever we are using, that will determine what we call the breaking strength. Okay. In fact, there is a chapter called Properties of Matter where we will understand how different materials break under different amount of stresses. Okay. But in this chapter, we'll assume that whenever we have a thread or rope or whatever in a system, it has not reached that breaking point. It's able to withstand whatever external forces are acting, and it's just in a normal situation where it's not going to it's not going to break out. Okay. Now let's understand one very important point about tension. So next is extremely important. Just a second. Yeah. So if we have a string or thread of negligible mass, that means its mass is very small, negligible compared to the other masses in our system. Like there might be a block attached, or we might be applying a force which is equivalent to the weight of certain amount of mass. So that is very large compared to the mass of the thread itself, or the mass of the thread or rope is negligible. Okay. In that case, it always, in every situation, it always has uniform tension. That is the same magnitude of tension, as uniform tension in magnitude at all points along its length. And we'll understand in a moment why this happens. Whereas a heavy rope or chain or that kind of material may have, so again, not necessarily always has, but may have, so we'll discuss in what kind of situations, may have variable, that means different amount of tension along its length. Now, this is a very key point in understanding how to solve Newton's laws equations involving systems which have threads or ropes or chains and things like this. Okay. So first, just make a note of this point, and then through some examples, I'll illustrate to you why this happens. Okay. That a massless, so-called massless thread or a thread or rope of negligible mass will always have uniform tension throughout its length. Whereas a heavy rope or chain or something like that, in certain situations, it can have variable tension. So what we mean by uniform tension is कि हर point पे tension का magnitude equal रहेगा. Whereas what we mean by variable tension is that at different points, the amount of tension might be different. Okay, so the simplest way of understanding this point is through this next example. So suppose we have this situation in our example, that we have a chain like this. Okay. So this is a chain. It has 10 links, and each link is of 1 kg. So it's a heavy chain. Okay. Mass. So the total mass of the chain is 10 kilograms, and we have attached a block of mass, let us say 20 kg. Okay, so hope you're understanding what we mean by links. Okay, so we will call this one the first link, second link, and like this. Okay, so I seem to have drawn too many links, but doesn't matter. Okay, so this one is the last, the 10th link. Okay, now we have to calculate the reaction force between the 10th link and the block. Okay, then the 9th and 10th link. Okay, then the 5th and 6th link. Then the second and first link, and the first link and the C link. Okay, so that reaction force that exists, that itself will be the tension over here. For a chain, that sort of reaction force that acts between one link and the next link, or the next point of attachment, that is what we call tension, because it acts along the length. Okay, so let's understand this. Okay, so hope you are clear about what the question is talking about. Okay, so now how do we calculate each of these forces? We will calculate it by free body diagram method. Everything in Newton's laws of motion is solved by free body diagram method. Okay, so next what we'll see is, for the first part, okay, the tension between, or you can say the tension acting at the 10th link acting on the block. So for that we will make a free body diagram of the block itself. So what we'll understand is, this block is being pulled up with a tension, let us say that is T10, and that is balancing its weight because its acceleration is 0. So this tension, this one, is becoming how much? It is becoming equal to capital Mg. So let's say that is 200 newtons, because we are taking G as 10 and the mass of the block was 20 kgs. Okay, so this is fairly easy to understand, nothing extraordinary in this. So I'll just compare this free body diagram to the above diagram, you will understand why this is the case. So EA block through its hook, it's attached to the 10th link over here. So that 10th link of the chain is applying how much upward force on it, this much. Okay. So this is the force of tension on the block by the 10th link. All right, this is clear. Okay. Now let us come to the second part, the tension between the 9th and 10th link. So for that, what we'll do is, we have a lot of options what we can do, but the one that I will take here, the option I'll take here is that, so now we want to find the tension between the 9th and 10th link. Okay. So for that, we'll make the free body diagram. Just imagine the FBD of the 10th link itself. Okay. So just imagine we have magnified the 10th link like this. Okay. So क्या हो रहा है? From below, the block is pulling it down with it this. Okay. This is equal and opposite to the force we had shown above. Whereas from above, the 9th link is applying a force of this on it. Okay, so this is the, okay, this is the tension force applied by the 9th link on the 10th. Okay, and this is the tension force with which the block is pulling down the 10th link. Okay, and of course don't forget that the thing has its own weight. So it has, let's say, a mass of m naught, where m naught is 1 kg. Okay, so now in this FBD the acceleration is 0. Okay, so when we write the force equation, what is happening, we will see that this force is balancing the sum of the weight of that link plus T10. So this force, the force on the 10th link applied by the 9th one, is equal to m naught plus capital M into G. And we have taken the mass of the chain to be 10 kg. Okay, so we can see that this m naught is nothing but total mass of the chain divided by number of links. Okay, so you can see that this is m by 10 plus capital M G. Okay, or in this case it is becoming how much? 1 plus 20, so 210 newtons. Okay, so just to illustrate this point a little bit more, okay, before you write this down, so यहाँ पे let's try to understand what is happening. This block, इस पे the 10th link is applying a force like this. Okay. Now similarly, the 10th link is experiencing a downward force like this and an upward force that the 9th link is applying on it. Okay. Similarly, the 9th link will experience a downward force that the 10th one is applying on it, and an upward force that the 8th one is applying on it, like this. Okay. So in this diagram, you can see that these two are an action reaction pair. This and this, they're an action reaction pair. Again, these two, they're an action reaction pair. Okay. So like that, between each link, In fact, it is like a normal contact force only here, but because it is between link to link of a longitudinal material like a chain, so we call it a tension only. Okay. So if the chain is replaced with a rope, for example, this is not like a contact force between links, but rather it is a force that acts along the fibers of the rope. The fibers of the rope are twisted together, and there is intermolecular force that is acting. So that internal force only that acts in place of this kind of reaction force between the links of the chain, that is called tension. Okay. So now logically we want to understand that how much is the tensional force acting on the 10th between the 10th link and the block. So for that we make the FBD of the block. So we understand the magnitude of this action reaction pair. So that's equal to the weight of the block, that was 200 newtons. But now what we want to understand, the next thing, the tension acting between the 9th and 10th block. So this action reaction pair, iska magnitude nikalna hai. Okay. Yeah, it will be correct, beta. Okay. So first, just make sure you're clear with these two FBDs. Then we'll come to the third part. And what this example is showing you is, because it's a heavy rope, or in this case, a heavy chain, the tension is varying. Link to link, the tension is changing by quite a significant amount. Right, Asmi, correct. So finally, fifth part will become how much then? Yeah, I'm coming to it, Asmi. Snikita, last part of second question I'm coming to, but first two parts are clear. Okay, now see, what I have done in the second part is I have made the free body diagram of just one link alone, and which link, that is the 10th link. Okay, but for that I have had to take help of the first part now, because I needed this T10 force also. Okay, but I can do alternately, I can do one more thing. I can also make the free body diagram of the combined object of the block plus the 10th link. I can make this combined objects free body diagram. So for that combined objects free body diagram, what will the forces look like? So this whole object will have a combined mass of m naught plus capital Mg, or that is 1/10 of the mass of the chain plus capital Mg, and there will be an upward tensional force acting on it, which is this force. This is the force on the 10th link applied by the 9th one, and its acceleration is 0. Okay. So then, without taking help of the earlier free body diagram, I can understand from this that the tension on the 10th link applied by the 9th one is vertically upwards, and it's equal to, which is 210. Okay. This thing comes directly. Okay. So this is a more useful method now, because then For example, we want to find the tension between the fourth and fifth link, or the fifth and sixth link. We don't have to keep drawing link after link. We can just make a combined free body diagram. So this is how we will deal with now the third part of the question. So in the third part of the question, we wanted to find the tension between the fifth and sixth link. So what we'll do is we'll make a combined free body diagram. So for the next part of the question, we want to find the tension between the fifth and sixth link. So we'll make an FPD of the combined object, which will be the block plus 10th plus 9th, like this, up to sixth link. Okay, so 10, 9, 8, 7, 6. So we'll have 4 links. Okay, so we have the block plus link number 10, then link number 9, then link number 8, then link number 7, then link number 6. Okay. So on this system, this is how the fifth link is applying a force. And similarly, above on the fifth link, the sixth one is pulling back with an equal and opposite force. ठीक है? Now ये system का combined weight को balance कर रहा होगा ये. So इसका combined weight कितना है? It is capital M plus 4 links. So it is capital M plus 0.4 times small m g. So it is 20 plus 4 into 10, or 240 newtons. Okay, so that is why the answer for the third part, the tension between the fifth and sixth, will be equal to 240 newtons. Okay, so this system's acceleration is 0. So that is what will now show me that the tension between the fifth and sixth, magnitude wise they are equal, and that is equal to 240 newtons. Okay, so if this is the fifth link and this is the sixth link below, okay, so this is pulling this down, this is pulling this up. Okay, so Harpriya, just see the language of it and you will understand. Combined free body diagram banaya of block plus 10th plus 9th plus like that up to 6th link. So there are how many links? There are 4 links. Okay, so that is why the weight of this is equal to how much? This. Consider किया है ना? Oh, sorry, there are 5 links. My mistake. So this should be 5. Okay. So this will become 250 newtons. Okay. So the answer should be 250 newtons. Yeah, it's the midpoint of the chain. So fifth and sixth. 5 links above, 5 links below, like that. Capital M is the mass of the block and small m is the mass of the chain. We had written that above, Ayush. Okay. So now similarly, when you work out the tension between, what was it, first and second, no? That will work out to be how much? That will work out to be 290 newtons. Okay. And finally, the tension at the first link, that will work out to be 300 newtons. Okay, people, so understood this example? So for this, you make the free body diagram of the block plus 9 links. That is link number 10 to link number 2. Okay. So that will show you that the tension acting on the second link due to 1 will be equal to capital M plus 9 M naught G, or capital M plus 0.9 times small m G. Okay. And similarly for this, make the FBD of the block plus the full chain. Okay. All 10 links. Yeah, you can do that way also. You can go on subtracting mass. We started from the bottom, you can start from the top and you can go on subtracting mass. You can do it that way also. So that way you will get this 300 newtons at the top first. And for example, for this 290, you can make an FBD of just the last link. I mean the first link on top. Then for the fifth and sixth, you can make the FBD of the first 5 links, link number 1 to 5. That way also you can do. So many ways of approaching this, but the point is it's showing you that because it's a heavy chain, okay, the tension varies from link to link. Okay. This was the question. Okay. So what we saw here, that this was 200 newtons. This was 210 newtons. This was 250 newtons. This was 290 newtons. And this was finally 300 newtons. Okay, so hope this example is clear to all of you. Okay, now in this same example, suppose we replace this heavy chain with a much lighter chain. Lighter chain doesn't necessarily mean a weaker chain. It can be made of stronger material, so it can still withstand. Okay. So suppose if this heavy chain is replaced with lighter one. Okay. So its mass is, let's say, 1/100th. So each link is 10 grams because the whole thing is 100 grams. Then what would happen? Then we would see the block is the same. Then what we would observe here is that T10 would remain capital mg, so 200 newtons. Okay, but this would become, okay, so that would become how much now? 10 grams. So that is equivalent to 0.01 kg. So into 10 it becomes 0.1 newtons. So this would become 200.1 newtons. Okay. Similarly, the tension between the fifth and sixth. Okay. The tension between the ninth and 10th, sorry, the first and second. So there's a much smaller variation in tension. There's still variation in tension, but it's much smaller. You can see. So the lesser the mass of the chain or rope or whatever, now we can see the lesser the variation in this tension is becoming. Right. Yes, that point is correct, Snikita. So now you understood, na? So as the links masses are getting added, but the links themselves are very small in mass compared to the mass of the block. So the gradual increase in tension as you're going up the chain is not such a large increase. You can see 200 से लेके 201 तक, it's a 0.5% change. Whereas earlier it was a significant change. It was going from 200 to 300. It was a 50% change. So likewise, if we were to replace the chain with a very light thread, so likewise, the chain is replaced here. So small m is now tending to 0. It might just be a few grams or not even that much. But mind you that the string or rope, the thread is made of strong material, so it can withstand the amount of tension. So in that case, what will happen is that the tension at this end, let's say T1, will be equal to the tension at this end because the mass of the rope is tending to 0. T1 will be equal to T2 will be equal to capital Mg. And that will be the same as the tension at any other point. Yeah, so small m was that much, no? No, each link was 10 grams, beta. Ask me. Each link was 10 grams. So that is why your T1 is 201, whereas T910 is 200.1, no? Like that. Huh? Yes, yes. Yes, yes. That's correct. No, in this case, the knots make no difference, beta. Because even where the knot is present, there is no mass involved, no? Yeah, so how we calculate that? Now, heavy rope is very much like chain. Okay? So, if it is a case of a heavy rope, just like you calculated for that string, no? Like that, for the chain, same way. So, tension, so let's take this as an example. Okay, in a heavy rope. Now, let's do a slightly different kind of example. Let's take a situation where, I said, no, it's okay. Let's take the same example. So this is a rope of mass 5 kg, let's say, and length 100 centimeters, heavy rope. And this is a block of mass, let us say, 20 kg. Okay. Now, if we are in general taking a point P, which is at a distance x from the end of the rope. Okay. So we want to find the tension at a point P for x to be 0, that is, it's right at the end of the rope. Okay. Then x equal to 50 centimeters, that is midpoint. Okay. Then let's say x equal to 80 centimeters, and finally x equal to 100 centimeters, that is the top end of the string of the rope. So we'll make the same free body diagram method. So for the lower end, just make the FBD of the block. For the midpoint, make the FBD of the half the rope plus the block. Just try this out, people. Yeah, that's correct. Take G as 10 only. Ask me, that's correct. You will get this tension. So for example, this one 0.5 L, na, half the length. So this will become M plus 0.5 M G. So this will become 225. Okay. Correct. Whereas this one, it's 80 centimeters out of 100. So 0.8 times the length. Two 40. Okay. So we can even develop a general formula. You can develop a general formula like this, that just take this only. So take the FBD of the combined object, that is the block plus X part of the thread. Okay. So the tension acting here as a function of X versus the weight. Now the weight will be capital M plus mass per unit length into X into G. So tension as a function of X will become like this. So from this you will get these values. Okay, people. So hope this example of heavy rope and all is also clear. Let's look at another example involving tension now. So this time we have this situation. So a continuous horizontal force is applied on this system. Okay, so just try this out. Very straightforward question. Yes, that's correct, Manas. Snikita, both correct. Arnav, correct. Parikshit, you have to check your answer. Asmi, correct. Yes, Nikita, your answer for tension is also correct. Okay, so let us understand the free body diagrams. So here tension will be acting like this. It will act backwards on this block and forward on this block. And whatever acceleration M2 has, the same acceleration M1 will have. So when we look at the block, excuse me, M1, the forces acting on it are tension horizontally, and of course there are vertical forces which will balance each other. And when we look at the block M2, because it's a massless thread, so the tension will have the same magnitude. Yeah, so I just got disconnected in between. So coming back here, sorry, this horizontal force F and tension acting backwards. This has the same acceleration A. Latent. Okay. So the significant equations are these ones, that for the block M1, we have P is equal to M1A, and for the block M2, we have F minus T is equal to M2A. So just add these two equations. So the acceleration of the system is the external force divided by the combined mass. So that will become 2 meters per second square. And substitute this in equation 1. So you'll get the tension or 30 newtons. Okay. And of course, you will also understand that N1 is equal to M1G. So that's 150 newtons. And N2 is equal to M2G. That is 100 newtons. They're normal reactions. See the free body diagram, Harpreet. So the block M1 has 3 forces acting on it, 2 vertical and 1 horizontal. The block M2 has 4 forces. Okay, so hope this part is clear. Any doubts with this question, people? Okay, now moving on to the next part. So we will understand what is called a simple Atwood machine. Okay. That's basically a system of single pulley. So this kind of a system is specifically called simple Atwood machine. Okay. So this is what is called a smooth fixed pulley. Okay. So three-dimensionally, let's say the pulley looks like this. So the fact that it is fixed का मतलब क्या है? That it's got a fixed axle. Okay, so this axle, it does not rotate. Okay, and smooth means that the surface of the pulley, that is this surface, it's frictionless. Okay, so the thread or the rope slips without any friction acting on it. ठीक है? So we will be studying rotating pulleys in a different chapter. ठीक है? So all pulleys in this section are smooth and fixed. Okay. Rotating pulleys will be studied later. In a chapter called rotational mechanics. So that's quite a few months down the line. So we don't need to worry. So any pulley that is given to us right now. Achha, Swami, in the previous question, how we calculated tension, we just substituted the value of acceleration in equation number 1. See in your notes, equation 1 was that T was equal to m1a ना, तो उसमें acceleration का value निकाल के भी substituted it. Okay, so first of all, understand what is this. Okay, and of course, this is a light thread. Okay, its mass is negligible compared to masses m1 and m2. Okay, now then we'll come to exactly what we are solving in the question. Okay, but this is what is the definition of a simple Atwood machine. It's one single fixed smooth pulley with a system of two blocks attached to a thread going around it like this. So very standard kind of system it is. That's called the simple Atwood machine. Yeah. The rod that goes through the axis of the pulley, that is called the axle. Like you have the wheels axle, no? Like that. Okay. Now in the given problem, suppose if m1 is greater than m2, okay, then find the accelerations of the blocks the tension in the thread. Okay. So if m1 is the heavier mass, it will go down and this will come up with the same acceleration. Okay. and because it's a light thread, so uniform tension will be acting throughout it. So ultimately what we will do is we'll solve the whole problem by free body diagrams. Okay. So we will make the free body diagrams for each of the blocks. So for the block M1, you can just show it as a particle also. You can see that there are two forces. Yes, that's correct, beta. There is tension acting vertically upwards, weight acting vertically downwards, and it's accelerating downwards. So keep in mind that because it's accelerating downwards, we will write the force equation as weight minus tension is equal to mass into acceleration, because the net force is downwards because the acceleration is downwards. So that's why M1 is coming with M1G's weight is coming with positive sign and tension is coming with negative sign because the acceleration is downwards. Okay. Whereas if you look at this second block, its situation is like this, that it's going upwards. So for it, what is happening? The tension is dominating over the weight. So because this is accelerating upwards, we will have to write the force with the sign convention that upward is positive. So इसके लिए force equation क्या हो जाएगा? Tension minus weight is equal to mass into acceleration. So that will be my second equation. Now once again, two equations, two unknowns, T and A. So solve them simultaneously and you will get the acceleration. Yes, both will have to have same magnitude of acceleration, because kinematics wise you can understand that by the time the block M1 is coming down by 1 centimeter, let's say M2 is going up by 1 centimeters, the thread's length is fixed. Yes, so just add the two equations and you will get acceleration, and then substitute the value of acceleration. So equation 1 and equation 2. So the standard method of solving them is eliminate tension by adding them. And then substitute this in any of the two equations. That will give you the tension. So you don't need to memorize these formulae, but you will be solving so many questions based on these kind of things. It will become obvious. Okay, so at this stage now I'd like to come back to the assignment, assignment number 2, and discuss any doubts and questions that you might have. So finish writing this down and send me the doubts you have in assignment 2. Okay. This is what I've received so far. Okay, so let's start with question number 3 then. Okay, so go through question number 3, people. We'll start with that. I'll be sending you a worksheet plus some questions from module, etc. The portion of the test is still Atwood machine, simple Atwood machine. Till today's lecture, that is the portion of the test on 16th. So third question is very similar to one question we've done today. Actually, you'll be able to work this out now. Okay. Now this system is on a smooth surface. Now suppose you're pulling this with a force F. Okay. And this tension is, what is it, T2. And this tension is T1. Okay. And the masses are given to you. So just write the FBD equations of each one. So for the block A, you will have T1 is equal to MA into acceleration. For the block B, you will have T2 minus T1. And for the block C, you will have F minus T2. Okay. So just solve these three equations for the three unknowns. Acceleration, T1, T2, three unknowns, three equations. Add them, your T1, T2 will get cancelled, you will get the acceleration, then substitute the acceleration in each of the equations, you will get T1 and T2. Okay. So that's this question. Then let's come to fourth question. So in question 4, you have a combination of two strings like this, 60 degrees and 45 degrees. So you obviously tied a knot at this position. And from that position, you suspended another string. The block attached. Okay. So let us say the tension in this string is TA. The tension in this string is TB. And the tension in this string is TC. So obviously from this you can see that the tension in C is equal to the weight of the block. Okay. And then next what you can do is you can make a free body diagram of this point, that knot point. So the net force on it should be 0 because it's at rest and it's a massless point. Okay. So on that there is TB acting like this, TA acting like this, and TC acting like this. So this angle is 60, this angle is 45 degrees. Okay. So use Lami's theorem. So TC upon sine 75 degrees should be equal to TA upon sine 135 degrees. And that should be equal to TB upon sine 150 degrees. Okay. And sine 75 you can solve like this. Okay. And in this, of course, TC is equal to mg. So substitute that, so you will get TA and TB. Okay, so hope this question is clear, people. Yes, people, is this question clear to all of you? Okay. Now, next, moving on to fifth question. Now, fifth is the only one I think in the assignment which is little bit tricky. So I'll discuss in detail. So in question 5, you have actually this triangular wedge kind of thing. Okay, this kind of an object is called a triangular wedge. Basically, it looks like a prism in 3 dimensions. It's an object like this. So this is what we call wedge. It's basically, it's shaped like a prism, triangular prism, that is. Okay, and in a 2-dimensional diagram, we just show it from the side. So you just see its side profile like this. So this thing, okay, so it's actually kept against a wall like this. Yes. This is the floor and this is the wall. It's kept like this against the wall. And of course, you have a smaller block on it and a thread attached. So the smaller block is kept like this on top of it, and there's a thread attached. And this angle is theta. Yeah. So obviously, so C part is the slightly tricky part. So let's understand all the forces first, okay, and the free body diagrams, because you will need that for the C part also. Okay. So there is tension in the thread. Okay. There is weight of this block. Okay. And this surface will be applying a normal reaction like this one. Okay. So then when you consider the triangular wedge, it will experience an equal and opposite normal reaction like this. It will experience its own weight, capital Mg. It will experience some kind of normal reaction or reaction from the wall. There is also normal reaction only. and some kind of normal reaction upwards from the floor. Okay. So now you make the two free body diagrams, one for the smaller block and the other for the wedge, and you should be able to solve it from that. Okay. So free body diagram for the block. So it's lying on this inclined plane, which is making an angle of theta with a horizontal. Okay. So it's vertically downwards is its weight. Okay. In this direction is the normal reaction, and this sort of direction is the tension. Okay. So what we'll have to do is now take your x and y axis like this and resolve mg. So to resolve mg, you can see this angle will be theta. So when you resolve mg, like we discussed last time, this component of weight will become mg cos theta, and this component of weight will become mg sin theta, and the block is at rest. So along the x-axis, what is happening? Tension is balancing mg sin theta, and along the y-axis, what is happening? Normal reaction is balancing mg cos theta. Okay. Now similarly, you make the free body diagram for the wedge. So on the wedge, what all forces are acting? Let's first write the forces like this. So there is normal reaction that this guy is applying, that is along this line. Okay. So if this angle is theta, you can see that this line is at the same theta to the vertical. Okay. So when I make the free body diagram of capital M, so this normal reaction force will be in this sort of direction, that is making theta with a vertical. This angle will be theta. Okay. And of course, the wall is applying a reactionary force like this, and the floor is applying a reactionary force like this. So those will show up here as this, and this. Okay. And now you just take components of this. So taking components of this, this will become n cos theta, and this will become n sin theta. Okay. So your equations here, this part, n sine theta will balance this. Okay. And reactionary force for the floor will balance n cos theta plus capital M. Okay. So you'll have to substitute the value of n from both of these. Small mg cos theta. So doing that, you will see. Okay. Yes. So the parts are a little bit interconnected. So you have to first calculate the normal reaction from the first free body diagram, then substitute that normal reaction in the second FBD so that you get the normal reaction of the wall and the floor, or the reaction force of the wall and the floor. Okay, people, so this should be clear. Now, see, ninth question you should be able to manage, because you will have to use the same kind of method that we did for this question number 4 earlier. Now, use Lami's theorem, uh, make the free body diagram of the block, and the two tensions are acting diagonally and balance with the weight. So Lami's theorem or components, whatever. So for question 9, you can just understand like this. Tension, they'll be same because the angles are same. So here these two angles will become theta each. That's why these two tensions will become same. Or you can start by taking T1, T2 different, but you will be able to prove that they are the same. Okay. Question 10, hope you have done. It's a little bit tricky. Use vector algebra in question 10. F1 plus F2 should become the net force. So in this is given, this is unknown, and that should be equal to mass into acceleration. This is also known. So use component algebra to solve. All right. Similarly, I think 11th question also should be able to manage. I'll just give you a hint for it. So ice surface is very smooth. Okay. So on that, there is a person of mass m1, let's say, tied to a rope, a block m2. So whatever force the person applies on the rope, that becomes the tension in the rope, and that acts on the block. Okay. So on the person, there is tension T. On the block, there is tension T. So the person has an acceleration A1, the block has an acceleration A2. Okay, so that tension is equal to F is equal to M1 A1 equal to M2 A2. So from this you will find out the accelerations. And once you find out the accelerations, you can use the relation that displacement of the person and the block will be half A1 T square and half A2 T square. And by the time the two of them meet, the sum of their displacement should become the length of the thread. So that's how you can deal with the 11th question. Okay. So with these hints, I think you should be able to complete. Any other doubts in the questions, you can discuss with me. I'll send you hints over WhatsApp. But I think if you go through today's lecture notes and try out the remaining questions, you should be able to solve them all. Okay, so I'm concluding today's session here, guys. Okay, and your test syllabus will be up to today's session, but there will obviously be a worksheet 3 I'll be sending. So you must complete that worksheet 3. Yeah, you will have to solve for time and eliminate time, beta, to find the individual displacements. S1 and S2 को आप time के terms में लिखे हो. Now S1 plus S2 should become the length of the thread. So find the time and then substitute it back in S1 and S2. ठीक है, understood, Aman?